Okay, morning everybody. Can you all let me know if you are hearing me, please? In the chat, please just indicate if you are hearing me by just typing yes. Okay, so Saeed is hearing me. Xavier, Kendall, Tyrese, Emily. Cool. Okay, so let's start then. All right. I can remember if we had reached number 4, right? So I will start from here. All right, so like I said, morning again everybody. All right, so this will probably be our mode of classes from now on until something changes. All right, so this is question 4 in the June 2013 paper. All right, for part A, it says state the law of conservation of linear momentum. All right, now you need to be very clear in all your definitions for physics. All right, so in the case of linear momentum, what we really need to say here is the total momentum, right, before a collision is equal to the total momentum after collision, provided that no external forces act on the system. So provided that no external forces act on the system. All right, so this is one of those definitions you just need to learn. Right. Part 2, describe a situation that demonstrates the law of conservation of linear momentum. So in this particular one, you can choose whatever example you want to give. You can give 2 cars colliding. You can give somebody shooting a gun. Right, when the bullet exits the gun, right, there's a recoil. The law of conservation of momentum applies there. The same thing if somebody's shooting a cannon, right? Even if you hold 2 bar magnets together and then you release them, the law of conservation of linear momentum also applies. So basically you can choose whatever example you want to give. All right. Now let's look at part B, right, which is the calculation. So in this case, we have a truck of mass 1250 kilograms, 1250 kilograms, right? It's heading north. It crossed the median on Jasper Highway and then slammed head on at 25 meters per second into a car heading south. All right. So let's draw a small diagram here as to what is happening. So you have a truck. So let's say this is a truck. All right, it's heading north and it's traveling at 25 meters per second. All right. Now, if you have to do any question involving conservation of momentum, you should draw a diagram. And like I said in class, we need to establish a direction and we need to say if it's positive or negative. All right, so this question they're talking about north and south. So the mass of the truck is 1250 50 kg, right? Now they said it has a head-on collision with a car. So the car is basically moving in this direction, south, and it's moving at 30 meters per second, right? And the mass of the car in this case is 625 kg. All right, so this is essentially what we have happening here. Now the question wants to know, what is the initial momentum of the truck, right? Now we know that the formula for momentum, P, is equal to m by v, right? The mass of the truck is 1250, so it's 1250 multiplied by 25, right? So all we do, we use our calculator to work this out. So that is 1250 multiplied by 25, and that gives us 31,250, right? So this is 31,250, and my unit is kilogram meters per second. All right, so that's the initial momentum of the truck. They also want us to work out the initial momentum of the car, which is P is equal to mv again. All right, the mass of the car is 625 multiplied by 30 meters per second, so it's 30. So again, we're using our calculators here. So that is 625 multiplied by 30, and that gives us 18,750. So this is 18,750 kg ms to the minus 1. All right, so we have the initial momentum of the truck, the initial momentum of the car. Now they said, assuming that the truck and the car move as one, right? So we've done a question like this in class. They move as one following the collision. What is the speed and direction of the wreck after the collision? All right, so I think I need a little more space for this here. So all of these momentum questions, we're going to start off by saying total momentum before the collision is equal to total momentum after the collision, right? Now you already worked out the total momentum, or the momentum of the truck and the car before, right? So the car is 31,250, sorry, the truck is 31,250. So the truck is 31,250. The momentum of the car was 18,750. So this is 18,750. So that's my total momentum before the collision. Now after the collision, they said they move off together, which means that they are moving as one wreck. All right, so my total mass of this wreck will be the mass of the truck plus the mass of the car, which is 1250 plus 625. So this is 1250 plus 625, right? And that wreck is moving with a velocity of v. All right, so now we have an equation here that we need to solve. So this will be, let's add this up here. So on the left hand side we have 31250 plus 18750, and you're going to get 50,000 on the left hand side, right? So this is 50, 1, 2, 3 is equal to, and on the right hand side we have 1250 plus 625. Oh wait, hold on, just now I made a slight mistake here, right? Just now, let's go back for here. So we need to establish a convention. Either we move in, when we move north we take it as positive, and when we move south we take it as negative. So I'm going to take north as positive, right? So if we take north as positive, it means that the truck, we'll take the truck's momentum as positive, so we'll keep this as positive, but the car is moving in the opposite direction. So sorry about that, this should be a minus, right? That should be a minus. So that is, let's do that, 31,250 minus 18750, right? So we'll get 12,500. So this is really 12,500. All right, and on the right hand side we're gonna have 1250 plus 625, you get 1875. All right, 1875 multiplied by v. So therefore my velocity is equal to 12,500 over 1875. So v is equal to which is 6.67 meters per second, right? And because we got a positive answer and we already established that we are using naught as positive, we say this is moving in a northerly direction. All right, now you're also supposed to do this for homework. Did you all get that answer? You can message in the chat. Yeah, so all right, Tyrese. So I made the same mistake too, all right? All right, cool. So let's move on to the next one. All right, so you need to establish a sign. How are we gonna do it, right? Okay, so let's move on to number 5. All right. So in this particular question, they want us to describe an experiment used to determine the resistance of a metallic conductor. All right. I believe at the last session or even the session before that, I gave you the diagram that we use to measure the resistance of a metallic conductor. Okay. So you all need to learn this circuit diagram for me, please. Right. So what we have now, they want us to describe the experiment, right? So we must always draw a diagram for this. So I'm going to draw a power supply, a battery basically. All right, and we're going to do this. We're going to put a variable resistor in the circuit so we can adjust our current. All right. Let's put our ammeter here. All right. Could also put a switch in the circuit if we want to. All right. And we need to connect our voltmeter in parallel. Right? So use a different color here. So this is the component that we want to find the resistance of, right? And we must put our ammeter in series. We must put a voltmeter across the component in parallel, right? Because that's how we connect a voltmeter. And we need to put a variable resistor inside the circuit, all right? So they want us to describe an experiment used to determine the resistance of a metallic conductor. So when you have a question like this, please write your answer in steps, all right? So that the examiner knows what you're talking about. So the first step, or the first thing I would do, is draw the diagram. You're going to get some marks for that. So set up circuit as shown in the diagram. Alright, so you set up the circuit as shown in the diagram, right? That saves you a lot of time trying to describe what you have to do. Alright, so what we do, we measure the current on the ammeter right, and corresponding voltage on the voltmeter, right? So we have basically I and V, right? The next step is we adjust the variable resistor. So we adjust the variable resistor, right? And we measure I and V again. So basically what we have to do is to get several values of I and V, right? And then what we do, we plot a graph, right, of V against I, right? Now if it's a metallic conductor, we know that we're going to get a straight line that's going to look like this, and the resistance is equal to the gradient of that straight line, right? So this is the experiment we use to determine the resistance of a metallic conductor, right? You need to know this experiment. Notice it's 6 marks for it. So you're getting marks for the diagram, and you're getting marks for giving some kind of explanation as to what we're going to do, all right? So this one. So in part B now, they give us a circuit here, right? What have they done here? Okay, so we have 12 volt battery, and we have 4 resistors, right? What do they want? All right, so they said given that the resistors R1 to R2 each have a resistance of 3 ohm, calculate the total resistance in the circuit. All right, so we know that this here is 3 ohms, this is 3 ohms, 3 ohms, and 3 ohms, right? And what do they want? Okay, so they want the total resistance, right? Now, when you have a question like this, you need to visualize what is happening here. So you see R2 and R3, which is, let's use a different color here. So these two resistors here, these two, right? These two resistors are in parallel. So what you need to do, you need to find that combined resistance first of all, right? So let's deal with those two, R2 and R1. So R2 and R1, I'm sorry, R3, right? They're in parallel, right? So remember there's a formula for parallel resistance. So 1 over RT is equal to 1 over R1 plus 1 over R2, right? This is just the formula. It has nothing to do with the labels they've given here, right? So 1 over RT is equal to 1 over 3 ohms plus 1 over 3 ohms, right? So 1 over RT is equal to 2/3. So this here is 2 over 3. So therefore RT, my total resistance here, is 3 over 2, right? Which is 1.5 ohms, right? So that's the combined resistance here. That's this. Now, the thing is, this resistor here, that's this one, and this one, and this new combined resistance here, they are all in series, right? When resistors are in series, we just add the resistances together. So my combined resistance here, so RT for the whole circuit, will be 3 ohms plus the 1.5 we got here, 1.5 plus 3 ohms, right, which is 7.5 ohms, right? So let's come back to the chat here. I just want to know if you all got that. One second. Cool. All right, so let's see, you all said you got the resistance I got there. All right, so that's the combined resistance, right? The hardest thing there is to visualize how the resistors are actually connected. So R2 and R3 are in parallel, and then R1, R4, and what you just calculated, those are in series. All right, now let's see what else they want us to find here. So they want you to find, so that's the total resistance. They want you to find the current drawn by the 12-volt battery. All right, so let's just check something here. So the combined resistance is 7.5. All right, so my combined resistance is 7.5, right? Which means that if I were to draw an equivalent circuit, right, it's going to look like this. I have a resistance here, one resistance, and this is 7.5 ohms, and this here is 12 volts, right? Now they want you to find the current drawn by the drawn from the 12-volt battery. All right, so all we're going to use here, we're going to use the formula I is equal to V over R, which is 12 volts, over my resistance here, which is 7.5. All right, and that will give me let's see, 12 divided by 7.5, and you're going to get 1.6 amps. All right, so that is my current being drawn from the circuit, right? That is the current here, that's the current flowing there, all right, which is 1.6 amps. The next part of the question now, they want us to find the voltage across R2. Okay, so let's come back to this diagram here. So you know what the current is. The current here is 1.6 amps, right? And you want to find the voltage across this here, R2, right? Now that 1.6 amp is actually flowing through R1, right? And then when it reaches this junction here, it's going to split into two. That current is going to be, some is going to flow here and some is going to flow here, right? Then those currents, right, are going to recombine at this point here, and they're going to pass through here. So the current flowing through R4 is 1.6 amps, right? So what we could do, we can find the potential difference across R1, right, by using V equal IR, which is 1.6 multiplied by the resistance of R1, which is 3. So that's 1.6 multiplied by 3, and that will give us 4.8 volts, right? So this is 4.8 volts. So that's the potential difference across, this is 4.8 volts. That's the potential difference across that. Now the current flowing through R4 is the same 1.6 amps, and it's the same resistance of 3 ohms. So this here is also 4.8 volts, right? I mean, you could do the calculation, but it's still 4.8 volts. So my potential difference across R2, right? So V across R2, right, will be equal to 12 volts minus 4.8 plus 4.8, right? So that will give me 12 minus 9.6, and that will give me 2.4 volts. All right, remember there are some rules pertaining to circuit diagrams. If we have a circuit that looks like this, all right, let's say we have two resistors in series here, and the voltage across my EMF of my cell is V, and the potential difference here across this resistor is V1, and the potential difference across R2 here is V2. One of the rules is that V is equal to V1 plus V2. All right, that's the concept I'm using here. So just message in the chat and let me know if you got 2.4 volts. Okay. right? So cool. So we got 2.4 volts, right? All right, cool. So most of you all seem to have gotten that, right? Next part, what do I want here now? Oh, okay, so that was the last part. No, did I miss everything? Okay, so yeah, so that's it for number 5. All right, so let's move on to number 6. So in number 6, they want us to describe an experiment to compare the ranges of beta and gamma emissions in aluminium, right? So, oh, and they want us to do it in aluminium. So what you should do in this particular case, you should draw a diagram, right? So we must have a source, right? Something needs to produce, so you have a source inside it, right? And we want to compare the ranges. So what we do, right, we're gonna put a sheet of aluminum. So let's start off with this. So we're gonna start off with beta particles. So we have a beta source and we have a thin sheet of aluminum, right? So this here is my aluminum, right? So we have a source of beta particles, we have the aluminum sheet. Next thing we need to have something to detect the radiation, right? So what we're going to use here, I'm going to use a GM tube, right, to basically measure the count rate on the other side, right? So what we'll do, we'll put the beta source here, and it's a fixed distance from my aluminum sheet, and then we're going to have my GM tube a fixed distance as well, and we're going to note what is happening when we put the aluminum sheet there. All right, so what we should do is record what the beta source is emitting without the aluminum sheet, and then we put the aluminum sheet and record again. All right, and we do the same thing, but we're going to use a gamma source after. Basically, we should know that the beta particles are stopped by a thin sheet of aluminum. All right, so this is a standard experiment in your textbook, right? So there's nothing difficult there. You just need to recall the experiment. Okay. Next one. In part B now, they said a liquid fluoride thorium reactor is said to be the new green nuclear reactor, right? So they said we write in this nuclear sequence to show how thorium-232 becomes uranium-233, a nuclear fuel, by calculating the numerical values of X, Y, right? So basically they've given us some nuclear equations here, right? And we need to figure out what the values of certain things are, okay? Now, when they give us nuclear equations, we need to remember that the total mass numbers on the left side must equal the total mass numbers on the right hand side. And the same thing for atomic numbers. So in the first equation here, we have 1 and we have 232, right? And you want to figure out X. So on the left hand side, we have a total of 233. So therefore, X has to be 233, right? Then we look at the atomic numbers. So you have 0 here and you have 90 here. So therefore, the total on the left hand side is 90. So therefore, Y has to be 90 as well. All right. So now, all right. So this is, so let's go to the second equation. So this is 233 and this is 90, right? And now on the right hand side, you have, this is 0 and you want to figure out what U is. So obviously, if your total on the left hand side is 233, then this has to be 233 as well, right? On this side, you have 90 on the left hand side, but you have a minus 1 here. So therefore, this number here has to be 91, right? So this is 233 here, and this is 91, right? Now, let's see what's going on the right hand side. So you have 0 and you have 233, so that's fine. You have 91 on the left hand side, but you have a -1 here. So therefore this Z has to be 92. Alright? So basically all we're doing is looking at the mass numbers on the left hand side, looking at the mass numbers on the right hand side, and we are comparing them. Right? So this is pretty straightforward, and look how many marks for this. You have 5 marks. It's an easy 5 marks. Alright? Now what's the last part? Okay, so the second part here now, we have an equation where we have, it's a fission reaction they're saying, right? They've given us the equation, and they said table 4 provides the data for the nuclides. So what they've done, they've given us the mass numbers of these things here, right? And we have to use that to calculate the energy released in the fission reaction. That's what they're asking here. Calculate the energy released in the fission reaction. Alright, how are we doing this? Let's see, I think, right. So what we need to do, we need to find the total mass on the left hand side of the equation, and we need to find the total mass on the right hand side of the equation. Alright, so on the left hand side, let's go. So on the left hand side, you have uranium-233, and we have the mass number here. So we're going to add, so let's do this, 233.03964. We're going to add that to 1 neutron, which is 1.00867. Alright, so that's all we have on the left hand side. So we're going to use our calculator. Now please do not round off too early. Right, we are dealing with extremely small masses here. Right, so 233.03964 plus 1.00867 equal. So on the left hand side, we're going to have 234.04831. All right. So that's on the left hand side. Then we need to go on the right hand side now. So we're going to add. First nuclide we've seen is this one, and the mass number is this. So we're going to add 132.91525. Add. You're going to add this one here, right? Which is this. And that is 97.91033. And then you also have, now you have to be careful with this, you have 3 neutrons being produced, right? So we're going to have to take this number here and multiply by 3. So I'm going to work that first, right? So that's 1.00867 multiplied by 3 equal, so this will give me 3.02604. Right? So this is my right hand side here. Right, so let's add that. Plus 97.91033 plus 132.91525 equal. Alright, so that answer is 233.85162. Alright, so we have the total mass on the left hand side, total mass on the right hand side. So what we need to do, we need to work out what we call a mass defect. Alright, so essentially we're taking the mass on the left hand side and minus the mass on the right hand side. So 234.04831 minus 235 minus 233.85162. Now because we are dealing with numbers to about 5 decimal places, it's easy to make a mistake. So 234.04831 minus 233.85162 85162, and my mass defect for this equation is 0.19669 U. Right, and that is, the unit here is atomic mass units. Right, now the thing is, we're going to use the equation equal mc squared, right, to work out the energy released. But the problem is, we can't use this number that we got here. This is atomic mass. I need to convert atomic mass into kilograms, and you see this here. This is how we're going to convert that to kilograms. So my mass, right, is really equal to 0.19669 multiplied by 1.66 by 10 to the minus 27. Right, now this is an important step. You need to remember that I need to convert my mass into kilograms. Sometimes in the question they actually give you the masses in kilograms, right? But pay attention. So multiply by 1.66 by 10 to the 27 minus equal. So that's going to give us one really big number, right? So we're going to go 3.265054 by 10 to the minus 28 kilograms. So that's my mass defect. Sorry, yeah, so that's my mass defect in kilograms. So now we're going to use equal mc squared, right, which is that mass there, which is 3.265054 by 10 to the minus 28, right, multiply by c squared, which is 3 by 10 to the 8. They've given us that in the question. So my final answer, so that's mass multiplied by 3 by 10 to the 8 squared equal. So this is 2.9385 by 10 to the 11 minus 11, sorry, not 11, right? So there's a minus there. Alright, so my energy release in the reaction is going to look something like that. Just message me in the chat, just let me know if you got that. Alright, just now I see Emily saying, so it's possible I made a slight mistake. Let's see, 1.00867. Yeah, actually, yeah, Emily's right. I made a, okay, so yep. Yeah, so I made a slight mistake there, right? So you all could just adjust your calculation accordingly, right? But that is basically what we need to do. We need to find the mass defect. That's the first thing we need to do. Once we get the mass defect, we need to convert that into kilograms, right? Once we convert it to kilograms, we're just going to substitute it into the formula, right? So, all right, so yes, I do have a slight mistake here, right? So my calculation is going to be slightly off. So the final answer, so guys, let me know what you all got for the final answer. Right, you don't need to give me the, we know it'll be same 10 to the minus 11, but what is the actual figure you all getting? All right, so Emily's saying we got 2.938. Let's see. All right, so 2.93. She said 2.93899. 2.93899. Right, so like I said, so I made a mistake here, so therefore the fifth decimal point, there's going to be a slight error. All right, but I just want you to understand the concept there. Right, so we okay with this paper? We're going to jump to June 2012. All right. Before I move on to the paper, do you all have any questions concerning this paper that we did before I move on? Alright, so since nobody has any questions, I'm not seeing anybody asking anything, I'm going to move on to the June 2012 paper. Alright. So, the first question in this paper, we have a student investigated the relationship between the electrical potential difference across the device and the current flowing through the device, right? So they've given us some values here. They've given us potential difference V, and they've given us current. But one thing I noticed, they didn't give us the units. So potential difference V, but it's missing a unit, and current, we're not sure if it's amps or milliamps, right? I can't tell from this. So what do they want? So the first thing they want us to do, they want us to plot a graph of potential difference versus current, right? Now make sure you all know what this means, right? Potential difference versus current means that we have to plot V on the vertical axis and we need to plot I on the horizontal axis, right? So basically we're going to plot all these values as 1, 2, 3, 4, 5, 6 values on a graph. So what I've done here, I've actually plotted the graph already, right? So we have voltage here and we have current here, right? And I've plotted the points and drawn a line of best fit through the points. Okay, so you'll have to draw the graph obviously, right? What else do they want here? Hold on, let me see what else they want. So they said calculate the gradient of the line obtained in A, right? And remember, I keep telling you this in class. When you draw a line of best fit, that line actually represents all of our data, right? So we should never use any points that we've plotted in order to find our gradient. Okay, so from your graph, let's see, hold on, one second. I see Aaron asking a question here. Yeah. So the experiment to compare the emissions, yes, it can be found in a textbook, right? So any textbook will have a description of how we're doing that. Okay. Okay, so they want us to calculate the gradient of the line. Now this is the first question on this paper, which is usually the data analysis question. So let's go to the graph, and we want to find gradient. Now, in order to find the gradient, we need to choose 2 points on the line. Okay, any 2 points you want. But what I would do, I would choose points that are basically wide apart so that I can use. Right? So let's see. I can choose this point here, right? And I can choose, let's see, I'm trying to use points that are easy to work with, right? So let's say this one here, right? You can choose any 2 points, but, right? So what you should do, you're essentially going to find the gradient of the straight line, right? Now your answer is going to be very slightly, depending on how accurate you draw your graph. So we need to know the coordinates of these points. So the coordinates of this point here on the right hand side, that is, let's see, 0.5246. So that is 0.56. So this point here is 0.56, right? That's the x value. And this is going up to, what is this? 41, 42, 42, right? And on this side here we have, what is this? 0.0246. So this one here is 0.08, and my y value here is 6, right? So these are the 2 points I'm going to use to find my gradient. So we know that gradient, right, is equal to my difference in y, so y minus y1 over x2 minus x1, right, which is equal to, so I'm going to go back to my graph here. So this is, so I'm going to take 42 minus 6. So I'm going to say 42 minus 6 all over 0.56 minus 0.08. 0.56, 0.56 minus 0.08. Alright, so let's hope I didn't make a mistake in the calculation here. So 42 minus 6 divided by 0.56 minus 0.08, and we are getting 75. Right? Now the thing is, the access to the gradient, so we got 75. We don't know the units, so I can't say if it's really ohms or not, right? So the gradient is 75. Now they said state the physical property of the device which the gradient is associated. Now remember, you plotted V against I, right? You plotted V against I, so we got a straight line, we worked out the gradient. So therefore the gradient, right, is really, so my gradient that I've worked out here is equal to V over I. So what physical property are you talking about here? The physical property we're talking about here is the resistance of the device. Right? That's my physical property, because we know that R is equal to V over I. Right? So 1 mark just for stating that. Now, what do they want here again? Now, using the information from the graph, comment on the relationship between potential difference and I. So, they're asking you to comment on the relationship. Now, you plotted the graph, or I plotted the graph, and I got a straight line, right? So, there's a linear relationship. So there's a linear relationship between V and I, right? So comment on the relationship. There's a linear relationship, right? And we could also state that the ratio V over I is a constant, right? These are all things you can say. It's a linear relationship. Ratio V and I is a constant. You say when I increases, V increases, right? So they want you to just comment on the relationship. Any one of these could work. Okay. All right, so next one. Draw a label diagram to show how the student could have connected his or her apparatus. Well, as you would realize, it's the same diagram as we did in the June 2013 paper, right? So, circuit diagram, we need a battery, right? We could put a switch, like I said. You need a variable resistor, so we can vary the current in the circuit. We need to put an ammeter to measure my current. Then we're going to have our device here, right? And this here is my voltmeter, which has to be connected in parallel. So this is the device we're talking about here, right? So this is the circuit diagram exactly as we did in the June 2013 paper, right? So cool. Next one. With reference to 1E, describe the procedure used to conduct the investigation. Well, you'd realize it's the same procedure that we did in the June 2013 paper. All you have to do here, you tell them you connect the circuit as shown in this diagram, right? You record I and V from the ammeter and the voltmeter, right? Then you use the variable resistor to change the current flowing in the circuit. And when you change the current flowing, you measure the corresponding value for V. So basically what we're going to have now is a table of values for I and V, right? And we're going to plot these values in order to get the graph, right? So the procedure is the same as the other paper we did. Right, so that's the procedure they want there. Now this one here now, there's 3 devices with resistances 8, 12, and 15 are connected in a circuit. Find the combined resistance of these devices when they are arranged in parallel, right? So visually, this is what has happened. So you have 8 ohms connected in parallel with 12 ohms. So you have a 12 ohm here. And then we have a 15 ohm. Right, so we have this. Right, so this is essentially what they're saying. Now we know there's a formula to find resistances in parallel. So resistance in parallel is found by saying 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Right, so 1 over RT is equal to 1 over 8 plus 1 over 12 plus 1 over 15. Right, so all I'm doing here is using the formula here. So 1 over RT equal, and you can use a calculator to do this. Most of you all in class, your calculator can do fractions. So 1/8 plus 1 over 12 plus 1 over 15, right? That gives me 11 over 40. So this here is 11 over 40. So therefore RT is equal to 40 over 11. So therefore RT is equal to 40 divided by 11. 3.64 ohms. Alright, so that's the combined resistance for 3 resistors in parallel. Alright, so please make sure you know that formula. Alright, so that's it for question 1. Alright, you all okay? You all following? Alright, so let's move on to the next question. Alright, so this is actually question 2. Okay. Alright, so they give us a table here in question 2 which relates to physical quantities and the derived SI units. Okay, so the first one, physical quantity area, and they want the derived SI units. Right, so area is basically a length multiplied by a length. Right, unit for length is meter, and you multiply by meter. So the SI unit for area is meter squared. Right, so my derived unit is meter squared. In the case of volume, we are multiplying 3 lengths. Length by another length. So therefore that's meters by meters by meters, which is m cube. Right, so the derived unit for volume is meter cube. Then they give us some derived units here, kg m to the minus 3. So kg m to the minus 3 is the same as saying kg over meter cube, but kg is mass and meter cube is volume. So mass over volume, you should know, is density. So this here should be density. Alright, so easy 3 marks here. This next one, state 2 fundamental quantities and their corresponding SI units. So you all need to know your fundamental quantities, right, and their units. So we have mass, length, time, temperature, and current. Right, there's another one, but I have 2 more actually, but we don't use that at this level. Right, so mass, the SI unit for mass is kilograms, length is in meters, time is in seconds, temperature is Kelvin, and current is in amperes. Right, so they only want 2. I've given you 5 here, so any one you want to use. So let's see, what are they asking here? Calculate the density of gasoline. So it's gasoline we're working with, and so this here is my volume and has a mass of 102 grams. So this is my mass. Right, so we know there's a formula for density, which is this: rho is equal to m over v. Mass is 102 and the volume is 150. Right, so it's 102 divided by 150, and that'll give us 0.68. 0.68. Right, but that's 0.68 and we must give it a unit. Now we're working in grams and we're working in cm cube, so therefore the unit will be gram cm to the minus 3. Alright, so that's my density of gasoline, 0.68 gram per cm cube. Right, let's see, what's the next part? Part 2. They said if 325 grams of mercury of density So this is mass, right? And this here is density, right? This is rho, and it occupies a certain space. Determine the volume of the space. So we know that rho is equal to mass over volume, right? So rho v is equal to m, right? And they want us to find volume. So volume is equal to mass over density, right? So v is mass over density. My mass in this case is 325 and my density is 13.6, right? So 325 divided by 13.6. So my volume will be 23.9 cm cube. Alright, so I'm working in grams and I'm working in cm cube, so it's 23.9 cm cube. That's the volume occupied by the mercury. Cool. The next one, they said calculate the relative density of gasoline using the density of mercury as a base quantity for comparison. Alright, so some students may not have never saw this before, but typically when we have to find relative density, right, and by the way, relative density has no units. You might see that in the multiple choice exam. Relative density is equal to the density of the object, right, divided by the density of water, right? That's typically how we work out relative density. But what in this question is saying, calculate the relative density of the gasoline using the density of mercury as a base. So if we're using the density of mercury as a base, they mean at the bottom here, we're going to use the density of mercury. So let's go back to the gasoline. So the gasoline was 0.68, right? So this is 0.68 was the density of the gasoline, right? And that is gram per cm cube, divided by, we're using mercury as a base. So let's find the density of mercury. What is that? 13.6 is the density of mercury. So this is 13.6 gram per cm cube, right? The grams per cm cube will cancel. That's why relative density has no units. So this is 0.68 divided by 13.6, and you're going to get 0.05. 0.05, right? And we have no units, so relative density has no units. All right. So let's move on to the third question here. So we have a yacht here, and the mass is 8,300, right? So you have a yacht on a trailer, basically. Determine the weight in air. Determine its weight in air, right? So please, there's a way to convert mass into weight. Weight is equal to mg, in which case my mass is 8,300, and my value for g, they told us g is taken as 10, right? So this is 8,300, and the unit for weight is newtons, right? So my weight is 83,000 newtons, right? Easy, straightforward. Now for land transport, the yacht is secured on a trailer, and each tire can support a maximum of 7,000 newtons. What is the least number of tires the trailer should have in order to support? So basically, you have this big boat on top of a truck, and you need to put tires, right? You already know the weight. The weight, we just got the weight as 83,000, right? So this is 83,000 newtons. That's the weight. And you need to figure out the least number of tires. But you know that each tire, right? So each tire supports a weight of 7,000 newtons. All right, so therefore number of tires, right, would be equal to, we need to take the weight of 83,000 and divide that by 7,000. So that is 8123 divided by 11.9. And you're going to get 11.9. 11.9, right? But there's a decimal fraction here. So the minimum number of tires, we're going to take that as 12 tires. All right. Alright, so I'll move on to the next one. That's part C. So they said many forces on the yacht many forces acting on it, right? It's an equilibrium, state 2 conditions, right? So state 2 conditions that must be satisfied for an object to be in equilibrium, right? So the first one that is most obvious has to do with moments, right? So the clockwise moments about a point is equal to the anti-clockwise moments about that same point. That's the first thing. So you have to say the sum of the anti-clockwise moments about a point is equal to the sum of the clockwise moments about the same point. You need to put this the same point. Right, so you can state that. We can also say that the resultant force acting on the yacht is 0, right? So if my resultant force is 0, then I'm in equilibrium, right? So those are the two things that you want there. State the effect that the position of the center of gravity of an object has on its stability. All right, so the position of my center of gravity affects whether I'm stable or not. Now here's how we know if so let me just tell you what we want here, right? So the lower the center of gravity, the more stable the object. Right? So this is what you're looking for. The lower the center of gravity, the more stable the object. Right? That's why high-speed race cars, they're very low to the ground, because you want to lower the center of gravity. Now, to know if an object is stable or not, what you do, let's say we had this object here and it's on a surface, right? And this is my center of gravity, right? That's my center of gravity. In order to determine if the object is stable or not, we need to draw a vertical line, right, that passes through the base of the object. That's here, right? If that line is in there, then the object is going to be stable. But if I do something like this, if I tilt the object a little bit, let's say I do this, right, and my center of gravity is here. If I draw a line, a vertical line here, that line falls outside the base of the object. This is the base of the object here. right? And this line falls outside the base. So this object here is unstable, right? So all you really need to know is that the lower the center of gravity, the more stable an object is. Okay. Next one here now. They want us to state Archimedes' principle. All right. So Archimedes' principle. It states that the upthrust. So my upthrust is equal to the weight of the fluid displaced, right? And that has to do with when an object is partially or wholly submerged in a fluid. Alright, so we can start the definition from here. When an object is partially or wholly submerged in a fluid, right, the upthrust is equal to the weight of the fluid displaced, right? So what we're saying is this. If I have, let's say this is water here, right, and I have an object underneath the water, the object is going to have a weight which is acting downwards, but because it's in a fluid, it's going to experience an upthrust, right? And because it experiences an upthrust, that particular upthrust is equal to the weight of the fluid displaced, right? So this is one of those definitions. You just need to learn it off, and it's basically this: when a body is wholly or partially submerged in a fluid, it experiences an upthrust, which is equal to the weight of the fluid displaced, right? Alright, so I just turn off the mic there for a sec, right? So the next part here now, they said the hull is made of steel, which has a density of this. Explain how it's able to float in seawater, which has a density of this. Alright, so look at this. Alright, so that's the surface of seawater, and we have the boat like this, right? This here represents the volume of water that's going to be displaced, right? So therefore we're going to have an upthrust here, and we're going to have the weight here, right? So explain how the yacht is able to float in seawater even though the density is this. So what you need to see, remember, upthrust is equal to weight of fluid displaced, right? That's the most important thing. Upthrust is equal to the weight of the fluid displaced, right? Now, if you want to increase the size of your upthrust, what you need to do, you need to displace more water. That's what you need to do. So they say explain why it's able to float, right? So the yacht displaces enough water right? Enough, well, seawater we're talking about here. Seawater, right, in order to experience an upthrust right, which is equal to the weight of alright, so that's essentially how we're going to explain this one, right? I've seen them ask a question like this where you have a big tree fallen in a river, but it floats. But if you take a nail and you drop it in the water, why does it sink? It all has to do with the shape of the object and whether it's able to displace a large volume of water. The more water you displace, the greater the upthrust. All right. So let's look at this one here. Where am I? Okay, so we want to calculate the volume of seawater displaced as it floats. Right. So, like I told you all, I have a feeling you might be getting an Archimedes principle question, right? So make sure you know how to do this. So let me see, where are my values? Okay, so the density of seawater is 1025, right? So let's go with this. So the density of the water is 1025 kilogram per meter cube, right? So that's the density of seawater. Now, we know the weight of the object. We worked that out already. So the weight of the object was, how much was it? We had worked out the weight in the first part of the question, which was 83,000. Right? So the weight is 83,000 newtons. Right? So look at what's going on here. So you have your weight acting downwards. This is 83,000. We have your upthrust U. Right? Now, calculate the volume as it floats. Right? Now, if it's floating, it means that the upthrust is equal to 83,000. Right? So upthrust is equal to the weight of the water displaced. Right? That's what my upthrust is equal to. Now, because it's floating, it means that my weight has to be equal to my upthrust, right? So my upthrust in this case is 83,000. So the weight of the water displaced has to also be 83,000, right? And therefore, we need to work out the mass of the water displaced, right? So the mass of the water displaced, right? Now remember, we know this formula, W equal mg, right? So mass is equal to W over g. So this is W over g. We're going to take g as 10, right? So 83,000 over 10, which is 8300 kilograms, right? Now, we also know that density of the water is mass over volume, right? Remember, you want to find the volume of the water displaced. So V is equal to mass over density, which is my mass here, which was 8,300, over my density for the water, which is 1025, right? So this is 8312 divided by 1025, and I'm going to get my volume as being 8 point, let's round this off, so 8.10 meter cube. Alright, if you all get a different answer, please let me know when you try it. Alright, Okay, so let's look at this next one here. This is number 4. Right, experiments into the fundamental nature of matter are being carried out at particle accelerator facilities. Right, 100 years ago, Geiger Marsden performed the now famous gold foil experiment at the suggestion of Rutherford. Describe this experiment and explain how it established the nuclear structure of the atom. Now, here's what you need to do. You need to draw a diagram when you have to explain this experiment. What we have an evacuated chamber. We have, so you have an alpha source. Right? We have a thin sheet of gold foil. And we have this here, which is, right, so you need to draw this diagram and you need to label it, right? So you have an alpha source, you have a thin sheet of gold foil, and so you have a thin sheet of gold foil, right? We have a microscope. We have the eye, and you see this here. This here is a slide coated with zinc sulfide. Right, and here we need to say it's an evacuated chamber. Alright, so you need to draw this diagram, right, and label the diagram. So what is happening is that we are projecting alpha particles at a thin sheet of gold foil, right? The purpose of the slide, which is coated with zinc sulfide, is that every time an alpha particle hits it, we get a flash of light. That flash of light we refer to as a scintillation. Alright, so this is basically the experiment, and this table here, this circle, right, what happened is that this could move right around the table here, right? So we can identify the location of alpha particles. Now, they want us to describe the experiment. You drawing this diagram and you saying this in words. Now, you need to explain the results of this experiment. So the first observation, most of the alpha particles pass through the gold foil. Right? Now, what does that tell us about the atom? Right? Most of the atom is empty space. That's basically what it's saying. So most of the atom is empty space. Right? That's the first thing. The second thing, some alpha particles were deviated, meaning they get deflection. So if the particle was doing, so if it was coming towards the gold foil, it did this. Right? So some were deflected. Now we know that alpha particles are positively charged. So therefore, this tells us something about the nucleus. So the nucleus is dense and positively charged. Right? So that's what it's telling us. And the third observation is that some return to the source. Right? So the only way that can happen is if the nucleus is extremely dense. Alright? So this is the experiment, and so basically after they did the experiment, what they were saying is that this here represent my nucleus, right? And the atom looks something like this, right? It has a very small, dense, positively charged nucleus, right? But most of the atom is really empty space, okay? So let's move on to this next one here now. It said one type of reaction in a nuclear reactor involves bombarding a uranium atom with a neutron, right? So we have this reaction here. They want us to complete the reaction. So again, we need to look at the mass numbers on the left hand side and figure out what this is. So on the left hand side, we have 236. So you have 236 on top here, right? On the left hand side. On the right hand side, we don't know what this figure is here. We need to figure that out. But you have 144. Now be careful with this because you have two neutrons here. So this will be, so you have 144 plus 2. That'll give me 146. And I need to take away that from 236. And you're going to get 90. So this figure here is going to be 90. Right? So let me just double check that. So that's 90 plus 144. Right, 236, right? Then we're going to do the same thing with the atomic numbers. So on the left hand side, we have a total number here of 92. But here we have 36, and we have, well, this will be 0. So it's simply 92 minus 36. So therefore, this here is 56. All right. All right, so we're going to do this one here now. So they gave us some data. They gave us the mass numbers for these things, and they want us to calculate the energy released in joules, right? So this is the equation we have here, and so we need to find the total mass on the left hand side. So we have uranium and we have a neutron, right? So we're going to add, so on the left hand side, we're going to have 235.118, and we're going to add that to one neutron. So that's 1.009, right? So that's my left hand side. Hopefully I don't make a mistake in this one like the last one, right? So 235.118 plus 1.009, and that'll give me 236.127, right? That's on my left hand side. On my right hand side now, what do we have on the right hand side? We have krypton and barium, right? And two neutrons. So we have krypton and barium. So that is 89.947 plus 143.881. And we have, it's two neutrons you have on the other side, right? So that'll be 2 multiplied by 1.009 equal 2.018. So this is 2.018. So we're going to add that up now. Plus 143.881 plus 89.947, and you're going to get 235.846, right? So that's what we're getting on the right hand side. So my mass defect now, remember what you're supposed to do. So mass defect is equal to, I'm going to take the 236.127 and I'm going to take away 235.846. minus 2 to the 6.127, 0.281. Right, and that is units. Okay, I'm back there, right? For some reason, a lot of music trucks passing on the road today. All right, so this is my mass defect, 0.281. So I need to convert that to kg. So mass is equal to 0.281 multiplied by 1.667 by 10 to the minus 27, right? So 0.281 multiplied by 1.667 by 10 to the 27 minus, and that will give me 27 by 10 to the minus 28, right? And that's in kg. So the next thing we need to do, we need to use the formula equal mc squared, right, which is my mass, which is this big long number here, multiplied by c squared, right? So I'm just gonna work it in the calculator one time, multiply by 3 by 10 to the 8 squared equal, and you're gonna get 4.21583 by 10 to the minus 11 joules. All right. So that's up to number 4. All right, so I've been doing most of the talking basically. So we're gonna stop there. I won't go for the full 2 hours, right? What I want you all to do is to complete this paper for me for next week, right? I might probably even give you a multiple choice exam to do as well. All right, I hope the session was fruitful to you guys. All right, so I really don't know what's going on today. There's tons of music truck that's passing on the road.